Let's go over one more exercise with the transistor. And in this case, we are going to have the resistors now connected in this fashion around the NPN transistor. The VBE is still equals to 0.7 and the beta equals to 100. And we want to find the voltages and the currents around the NPN transistor. As always, I start by designing our circuit. Sometimes this is useful because you can design the circuit in a way that it's familiar to you and it helps analyzing the circuit and writing down all the relevant information that I need to analyze the circuit. We have grounds connected here and we have 100K and 50K connected on these resistors. VBE is equal to 0.7 volts and beta of 100. Now, if we look at the circuit, we see that connected to the base of the transistor, we have a voltage divider. And we need to be careful here with this voltage divider. We're going to analyze this circuit in two different ways and see the difference. And I'm going to just redesign that voltage divider really quick here. So we have the 100K resistor, the 50K, and the reason why we need to be careful with the voltage divider is because the current that it's actually flowing to the base of the transistor is equal to zero. Is not equal to zero, sorry. And with that in mind, the voltage divider is not the way to go. And we're going to need to apply a different technique. And in this case, we can use the Thevenin equivalent. And we're looking at the circuit from this point of view. So we want to find the Thevenin equivalent seen from that point, meaning I'm going to find the Thevenin resistance and the open circuit voltage of my circuit. All right, cool. So our Thevenin is going to be equal to the parallel between the 100K and the 50K. In order to do this, we short circuit all the voltage sources, and this gives you a value around 33.33K. And the open circuit voltage, it's going to be the voltage divider of your 15 volts times 50 divided by 150. The K's cancel out and you get 5 volts as an open circuit voltage. Alright, so let me redesign the circuit now with the Thevenin equivalent. And the resistor at the emitter and the collector are the same. And now I connect my Thevenin equivalent at the base of my transistor. Let's just write the values here. 5 volts, the R Thevenin, 5K and 3K and 15 volts. All right, so now we can start analyzing our circuit. We can apply KVL on our loop here in this point of the circuit. And if I do that KVL, I'm going to get the following expression. The voltage drop across the power supply, 5 volts, minus the voltage drop across the R Thevenin, plus or minus VBE minus VE. And then if I rearrange the equation, I have it in this form with all positive voltages on that side of the equation, on the right side of the equation. And now let's write what we know. VBE, we know it's 0.7. We know that R Thevenin is 33.33K. And now we're a little bit in trouble here because we have one equation and two unknowns. So we need to find a way of solve our equation for one of the variables here. And we're going to assume that the transistor is in active mode. And in active mode, I know that my IE is equal to the sum of IC plus IB. and IB is also related with IC by this equation, and substituting here I can find a relationship between IE and IB. The reason why it's important to find a relationship between IE and IB is because VE depends on IE. So VE is equal to IE times 3K. And now my IE is beta plus 1 times that 3K IB. And now I have one equation with one unknown, which is my current at the base. So I can rewrite this equation. Let me put find the common factor here, IB, factor these things together. All right, and now if I rearrange that equation to find IB, you're going to get an IB of 12.79 microamps. And let's highlight that answer. We can also highlight our Thevenin resistance and open circuit voltage for our Thevenin. Now that we have our IB and we assume that the transistor was in active mode, we can start calculating the other currents. Let me just go here and calculate VE because I know my IE. Oh, I still don't know my IE, but I'll put here my VE. Sorry about that. And the IE is coming from the relationship that we just know, which is beta plus 1 times IB. And you get a current flowing through the emitter of 1.29 milliamps. All right, with that current, then you plug up to find that VE. All right, let's keep going and find now the current that flows through the collector. And I know that it's related with IE using the alpha parameter. And I get a current of 1.277 milliamps. All right, cool. So we know the current flowing through the collector, and I'm going to design that current in the circuit, and I can now apply Ohm's law across the 5K resistor to find VC. So my 15 volts minus VC equals to the current times the resistance, and rearranging all these, I get my VC, which is equal to 8.615 volts. All right, sorry that I need to highlight these because it helps me with the equations that I need to do. And in active mode, I know that VC needs to be greater than VB, and VB needs to be greater than VE. If I put those values, VC is 8.615, and I'm actually missing VB. I didn't calculate it because I didn't need it so far. So let's calculate that VB, and we know that VB is related with VBE. So VBE equals to VB minus VE, and from here I get a VB of 4.57 volts. All right, let's plug that there, and my VE is 3.87. Highlight helps, and I'm in active mode, so my assumption is correct. Everything is good. So now the only thing that I'm missing is, oops, I should have done VB. The thing that I'm missing is VC. So let's calculate VC, which is equal to VC minus VE, which gives you a value of 4.745 volts. All right, so all these was by using the Thevenin equivalent for that voltage divider. And now let's just go back and repeat our math, but just assuming the voltage divider. So assuming that the current flowing through the base is very small compared with the voltage that flows through the voltage divider, and let's see which values do we get. All right, I'm just going to write these for us to follow what I'm doing. And we have now the voltage divider. The current that flows through the base is considered 0, so that means that that point is the VB. And I can apply directly my voltage divider, which it's equivalent to calculating the open circuit voltage for your Thevenin, which is 5 volts. The case can cancel out. All right, so I know VB. I can find my VE because I know VB is the same, 0.7 volts. Rearranging this equation, and I get a VE of 4.3 volts. All right, again, be patient here with me. I need to highlight, makes it easier to follow things. Also good practice if this is being graded. All right, so now that I know my VE, I can find my current IE, which is simple as VE divided by my 3K, and I get 1.43 milliamps, and my current flowing through the collector related with IE by multiplying by alpha, or multiplying the emitter current by alpha, and I get 1.4119 milliamps. Current flowing through the base, again active mode, and we get 14.19 microamps. And let's calculate now the voltages, so I can apply Ohm's law across the 5K resistor. So this equation is coming from the transistor, not from the voltage divider. And I get 7.905 volts. All right, so again, highlighting here the results. And the last thing that it's missing here for this one is VC. So let's find VC. I'm running out of a marker. And VC is VC minus VE, and I get 3.605 volts of VC. So if I put the results here side by side, the Thevenin results and the voltage divider results, both have the transistor working in active mode. So VC is greater than VB and VB is greater than VE. And at first glance, we see like they might see that the values are very close. So we might be inclined of using the voltage divider rather than Thevenin. I recommend doing the voltage divider just to get an idea where the transistor is operating. But then if you want a more accurate operating point, just use the Thevenin. And we can actually visualize that if I plot that information here on the graph where I have VCE on my x-axis and the current flowing through the collector on my y. I'm just pointing here the middle point of this load line, and the Thevenin equivalent is this white dot, and the voltage divider is this blue dot, and you see that the operating point gets shifted by applying the voltage divider. And this can make a difference, because if you are operating your transistor very close to saturation, when you calculate your parameters using your voltage divider, you might think that it's in saturation, but it's not there yet. In reality, even if the Thevenin equivalent is operating very close to saturation, you don't want that to happen. You bring that operating point down, either to the middle point or even lower than that. And that's why the voltage divider is acceptable as a rule of thumb to kind of understand where the transistor is operating. And let's go and simulate these now in Falstad. All right, I'm going to include my PNP transistor and the respective resistors around. All right, put some points here to measure the voltage and the current. And now let's go over multisim. And multisim, we can use multisim if we want more accurate more accurate results. And let's build the same circuit with multisim and validate our answers. All right, just placing here some measuring points, voltage and current. I actually need to move that current meter. I cannot put it on a node. I need to swap with that voltmeter. Let me put the measure the volt at that node and the current through this branch. Press play, and you see that the results are pretty close to what we calculated. Remember that we're using a different VBE, but we have similar results.